Hello everyone, my name is Apurva Narde. I'm a junior undergraduate student at Rutgers University. Today I'm going to be presenting my Monte Carlo study specifically investigating inclusive differential jet shapes at weak energies. Jets are a signature for the existence of quarks and gluons. Jets are special for heavy ion collisions because we see effects interaction between the heavy ion medium, the QGP, that is produced in these heavy ion collisions because jets are interacting strongly. Jet quenching is the phenomena that is associated with the energy loss of a jet as it travels through the QGP medium, and was first observed at the relativistic heavy ion collider, which is located at Brookhaven National Laboratory, and subsequently confirmed at the Large Hadron Collider, which is near Geneva. Here I'm investigating the possible biases in the jet definitions at Rick energies. Because different experiments use different definitions, they use charged jets, triggered jets, full jets, etc. The goal of this study was to determine whether by varying the jet definitions that I'm possibly creating modifications just due to the change itself. Here in equation 1 is you can see the differential jet shape variable, and in figure 1 this is the cartoon that represents the differential jet shape approximately. For the analysis, we simulated 40,000 proton-proton collisions within the Pythia event generator. I analyzed these particle collisions using the Rivet framework, which is written in C++ and Python. As you can see in figure 2, the distribution of the eta phi distribution of all particles is here, and in figure 3 is where we reconstructed our jets using the jet algorithm, and uh, as you can see, the distribution is uniform. Also, notice that there's a drop in the number of particles because at weak energies, most of the particles are generated in the mid-rapidity region. Nevertheless, the jet distribution is more uniform within this, plus or minus 0.6 units of rapidity. This is the PT histogram of the jets that were generated, and after applying some experimental cuts, you can see in figure 4, these are the full jets after selection, and these are the charged jets after selections. Here in figure 7, we have the integrated version of the jet shape. Um, in this figure, we have the blue histogram, which is the charged jets, and the orange histogram, which is the full jets. And these are the jet shapes that are reconstructed respectively. What we first observe is that this distribution is steeply falling. This is due to there's a large fraction of particles near our jet axis, and it drops as we look further away from the jet cone. And the same is true for both charged jets and full jets. But if we just look at the fraction of the particles that we lose by making charged jets in comparison to full jets, the ratio shows roughly that we lose a lot more in the core, for example, when we go from one jet definition to another jet definition. And then I looked into this further by looking at constituents for a wide variety of bins. And these are the selected PT region for these constituents, starting with 1 to 1.5 GeV constituents, 3 to 4 GeV constituents, 4 to 6 GeV constituents, and their respective jet shapes uh, for full and charged jets, respectively. What we notice is that when we compare charged jets to full jets within the same PT selection for high PT ratio, it's roughly 1. Whereas when we look at the softer cases of PT regions, the differences start becoming more and more noticeable, as you can see in the ratios. By sticking to our jet definitions in a rigorous way, both proton-proton and heavy ion collisions have a meaningful observation in the jet modifications, especially in the regions where we have high sensitivity, which is the low PT regions. Jet definitions play an even bigger role. Maybe in the high PT case, where it's possible to reach LHC energies, we might not have to worry as much because the minimal differences between the jet shapes and the charge versus fulls that we observe. Thank you so much for watching. I'll be happy to take any questions you have. My Zoom will be on Saturday, October 31st from 4 to 4:35 p.m. Central Time. Thank you.